Welcome to Convolutional Neural Networks in 10 minutes. This is a cat. Actually, it's a picture of a cat to be precise. Beautiful, no? Meow. This picture of a cat is in grayscale, as you may have noticed. Now, look closer. No, closer than that. What is this picture of, really? Why, you see those little boxes? You see how everything is becoming blurry? Those little boxes are pixels, and the picture is just a collection of pixels. Pixels in grayscale define a picture in little bits according to x and y coordinates, with the value corresponding to its brightness in grayscale. A value of 0 denotes blackness, or all the colors combined. The highest color, often 256, suggests all the colors, aka white. The slice of pixels we're looking at could therefore be represented with a simple matrix, like this one. Matrices are the building blocks of machine learning, and that's how our modern world has produced facial recognition, self-driving cars, and Instagram filters that make you a puppy. But how do they go about looking at a matrix of pixels and determining if it is a cat or a dog? In this video, we'll learn how. It starts with a filter. Filtering groups of pixels in the image is called convoluting them in deep learning terminology. This is how we get the phrase convolutional neural networks. Our filter is applied over the matrix in groups to return a transformed output. In this example, the filter is a 3x3 matrix, so it is applied to the pixels in groups of 3. To cover the whole image, it must move across and down until the whole image is covered. Notice that the edge of the filter was shifted 3 times. That is for 3 cells apiece. This gives the filter a stride of 3. The size of the stride can be changed as a hyperparameter of a convolutional model. A filter simply applies an element-wise multiplication to the pixel group, resulting in the matrix the same size as the filter, then adds them up, resulting in a single value. We run that filter on each 3x3 group, moving with a slide of 3, we get a 2x2 matrix representing our output. So that's how a filter works. But how does a filter help to tell a neural network what is a cat and what is a dog? Well, the numbers in the filter itself are actually changed and learned by our machine learning algorithm. This results in filters that can recognize features of an image. In our example, this particular filter could detect a vertical edge. If we had half black, half white image, and we applied our 3x3 filter, this time using a stride size of 1, we would see the following result. Our model could then learn that items which interact with the filter in a similar way all possess a vertical edge. If you're trying to imagine how a predictive model could turn this simple filter into a cat or a dog, imagine many filters, each possibly learning a different characteristic of the image, batched together in the single layer. This is a true power of convolutional neural networks. But before we can start batching things together, let's look at some other interesting characteristics of filters. The filter stops when it reaches an edge. Notice this means that the inner square block is giving input to every single filter output, while the outer corners only impact one apiece. This isn't just unfair to those poor cornermen. It also means our models might be erroneously too invested in those special little middle pixels. To correct this, we can add padding, like so. This gives our filters more room to run, resulting in a larger output and more impact for our edge and corner pixels. A fun little side effect of padding is that if we add enough, we can make sure that our output is the same size as our original input. This is especially useful when applying our many filters across many layers. If we shrunk the output each time the filter was applied, it would be pitifully small by the time we were done. So pitiful, the poor thing. But how do we know how much padding to apply? Well, it depends on what we want. This is not a one-size-fits-all scenario. However, if we take n for the length and width of our output, which we shall for sake of simplicity assuming a square matrix, we also take f for the length and width of the filter, and p for the length and width of the padding, and finally s for the length of the stride. Our output will be of size n plus 2p minus f divided by s plus 1. Now, jot that down. I'll wait. Now that we understand the calculation for our output size, is there a quick way to discover how much padding is needed in order for our output to remain the same size as the input? What a clever question. Indeed, there is. The size p of our padding layers is equal to f minus 1 divided by 2. Notice we subtract 1, then divide by 2. Do you know what this means? It means it works fabulously well if f is an odd number, but less well, in fact, if it is even. For this and a few other reasons, it is best to keep our filter dimensions odd. To recap, these filters we apply are convolving the input, creating convolutional layers. But there is more to a convolutional neural network than that. In fact, we still need a few key ingredients to make them effective. One of those ingredients is the pooling layer. Don't think of a swimming pool or a pool table. Instead, imagine it's the end of a long night with some friends, and you're pooling your money together for some delicious dominoes. Pooling layers help to reduce computational size and seem to improve the amount of signal our model detects. They work in a similar way to our filters, except instead of an element-wise sum product, a simple computation is performed over the pixel group instead. The most common computation by far is a max, as in max pooling, but average pooling is also used. Another important distinction is that in our filters, our parameter numbers are decided and learned by the machine learning algorithm, whereas max pooling is simply a calculation. There is no learning involved in this layer. To compute our max pool, we must pick the hyperparameters, which should be quite familiar by now. F is the size of our max pooling filter, and S is the size of our stride. If we apply a 3x3 filter with a stride size of 1, our result will look like this. Notice the output size is the same as if we'd applied a regular convolutional filter. Don't worry, you can recycle that same formula to determine the output size. You did write it down, didn't you? By the way, the first max pooling layer, by convention, comes after the convolutional layer. So often it is considered part of the convolutional layer. Now, so far, we have been working with an example of grayscale image. You may have noticed that some images have colors as well. So how do we account for that in our modeling? Well, take our original matrix. Its numbers represent shades of gray. But what if they were shades of green? Well, then we could combine those shades of green with shades of red and shades of blue to represent any color image in the popular RGB color space. Of course, now we would have a three-dimensional input matrix, also called a volume. We'll need to keep this in mind when shaping our input vectors and choosing our convolutional layers. In Keras, this means we need conv3D layer instead of conv2D. Now remember, we said we can apply multiple filters at a time. Well, when dealing with three-dimensional layers, we can apply the same layer to each hue, resulting in a three-dimensional output. Or, if we want to be specialized, we can also apply individual filters on each hue. This is how convolutional layers handle many filters simultaneously. It all gets stacked into that third dimension, which we sometimes call the channels of the layer. Now, we've learned a lot. But if we need to go all the way and create our convolutional neural network, we need one more element. So far, we have a three-dimensional input, three-dimensional filters, and max pooling, the result of which is a three-dimensional matrix. Now, how do we turn that three-dimensional matrix into a simple way to classify an image as a dog or a cat, or a hot dog or a not hot dog? Well, we unwrap the final output of our layers into a special layer called a fully connected layer. This is a transformation of the 3D convolutional layer output into a simple 1D dense layer. It simply unwraps all the cells from that output from 3 dimensions into 1. Then we can apply a simple logistic sigmoid activation to label the image as in fact not a hot dog. Or we can use any activation function we please. Now that we know the underlying structure of a basic convolutional neural network, it's important to zoom in and really understand what our robot friend, the algorithm, is doing. Notice our convolutional layer and fully connected layer are distinct in color. This is because they include the parts of the model actually being tuned by said algorithm. Let's look closer at how that works. Despite their differences, both convolutional layers and fully connected layers are just different types of artificial neural network neurons. This means, by convention, they both take some input, multiply it by a set of weights, add a bias, and activate it with a nonlinear function. In the case of the convolutional layer, remember each group of inputs for each stride gets multiplied by the weights in the filter, and a bias is added as well. For simplicity's sake, I've shown this one as a simple matrix multiplication with a bias. After that, a nonlinearity or activation function is performed. In this case, the rectified linear unit, or ReLU. Now let's look at the fully connected layer. Remember, our input in this case was a 3-dimensional volume that was stretched into a 1-dimensional vector. It doesn't always have to be this case though. Fully connected layers can also come after one fully connected layer or any other layer preceding it. Regardless, we have our 1-dimensional output and multiply it with a 1-dimensional set of weights. But instead of an element-wise multiplication per group and filter like in the convolutional layer, each item in the fully connected layer is multiplied by each weight. So the weights for this layer are of somewhat arbitrary length. This also has a bias term added. Note the bias is the same size as the input, not the weights. And then a nonlinearity is performed. In this case, we chose the sigmoid function. It is through these special calculations that our optimizer utilizes backpropagation and learns the parameters for our classifier. Now in the real world, our networks won't have the exact same structure as what we've just described. One impactful convolutional neural network was AlexNet, whose architecture looks something like this. This was one of the first models to generate hype for deep learning in the early 2010s. As you can see, effective convolutional neural networks are often quite complicated and involve many parameters in the real world. Luckily for us, for many use cases there is likely a model already trained in a similar way. Using transfer learning, one can freeze some or all of the weights in the original model and then add a final layer. This way, you can take advantage of the filters created by these models that might recognize features useful for your problems. For example, if you wanted to train a model so that your cat's bowl only dispenses food to your precious Fluffy, and not that annoying Maine Coon Max next door, you could use a model that had already been trained to recognize cats, and thus understood cats' features before tuning it just right to recognize your Fluffy. I hope you've enjoyed this introduction to convolutional neural networks in 10 minutes. If you did, consider liking and subscribing. We do appreciate it. Good day.